with the roaming microphones. So if you do have things that you want to ask our speakers about today, please hold on to them. As I begin, please let me acknowledge the traditional owners of the unceded lands on which we meet. That's the Wurundjeri people of the Kulin Nations. I'd like to pay my respects to their elders, past and present, and welcome any member of any Indigenous peoples here today. Thank you for joining us. We're very privileged to be able to hear today from Peter and Richard. I mean, I presume that most of the people here in the audience today first heard about this event online, and that illustrates to me exactly what it is we're talking about. Namely, we have this technology that mediates almost all our interactions with the world, the events we attend, the places we go, our ability to travel, our social networks, our shopping, everything. And of course, this technology had a seed and a point of origin, which was not terribly long ago, and we'll be hearing about that origin today. And there's another surprising element about it to me. If I think about the very first motor cars, and you can see photos of them from the 1890s, they had an engine, a gearbox, a transmission, they ran on petrol, and despite being in some ways drastically different and having very different shells, there is a core that is exactly that first technology that emerged in about 1885 and was in some ways fully formed within just a few years. And although the pictures we may see of computers today don't in any way hint at the computers we've all got in our pockets or sit down in front of or carry around in our bags, that nonetheless that core, engine, transmission, etc. remains in a very principled way completely unchanged. So hearing about how those very first machines appeared, hearing about the things they were used to do, hearing about how they developed into that next generation is what today's lecture is about. We have two fabulous speakers. I'm going to let them introduce themselves, but we have Peter Thorne and Richard Gillespie, and first up is Peter Thorne. Peter.
Thank you, Justin. I'm a sort of tribal elder, I guess, having lived through pretty well all of that revolution, being in my 80s, and we can really date a lot of this back to 75 years. And I must say, and it always occurs to me when we're talking about the acknowledgement of country, that the history that I'm fascinated in is the Industrial Revolution forward. And I really have a lot of trouble getting my mind around 65,000 years. It seems to me that's 1,000 times the history that I'm going to talk about today. And I think it's deep time and something that we probably don't all understand yet as to all the implications of it. And some of you may have seen a letter I wrote to The Age about that about 2 weeks ago. Okay, well, our story, and I'm not going to go back to Charles Babbage, founding person in the computing industry who built a computer that was never finished, blamed the client, and was generally irascible, and therefore set the ground rules for all later major computer projects. I'm not going to go back really to Turing, although he laid down some of the groundwork, as we know, before the Second World War. I'm going to just go back to Trevor Pearcey, who arrived in Australia on the end of 1945, straight after the war in England. He was a bit upset because he'd missed Christmas Day, because he crossed the international date line on Christmas Day on a very uncomfortable aircraft coming from the States. And it always seemed to me he jumped forward a day, and as we'll probably see, in some ways he jumped forward more than a day in his lifetime. He jumped forward years. He was still only in his 20s, and he was the archetypal boffin of the time, what we now call a nerd. He was tall, bespectacled, a POM in an Australian environment, pedantic. But he must have been pretty persuasive, because he persuaded radiophysics in Sydney that they should build a stored program electronic computer. And nobody in the world had built one of these at this stage. However, they got to work. They were a very interesting organisation, and there's a lot of links which Barbara Ainsworth, Monash and I have looked at back into whether or not there are links directly into Bletchley and to the people there, how he was influenced. But anyway, they had excellent electronic engineers at radiophysics, and they built the largest electronic machine that had ever been built in Australia. And by 1949, the end of 1949, they could run a test program. Now, they weren't the first, because in England, people were more directly connected in a way to Bletchley, had run the first store program at Manchester, and then later one was at Cambridge, and of course there'd been a computer in the States called BINAC. BINAC was a bit of a disaster. It's only spoken about in hushed tones because the client didn't seem to accept it. I think the manufacturer blamed the installers blamed the manufacturer, and they both blamed the transit company that moved it from point A to point B. But anyway, BINAC was not a success. So we can perhaps claim in Australia we built a successful store program computer before the US. And Australia had entered the digital age back there in at the end of 1949, and there was Trevor standing in front of the machine which they imaginatively called the CSIR Mark I. That was the sort of thing you called computers in those days, in Sydney. And there it is. It was a very well-engineered machine, because they were mil-spec in modern terms at radiophysics, and it was the best engineered. And I've looked at certainly in the replicas, in some cases the designs of the English machines, and they looked pretty ratty compared with this. This was and you can still see it was well engineered, and it had, of course, the longest working life of any of them. And anyway, it was used for scientific calculations, and by 1950-51, it was the first computer in history to play music. The birth, if you like, of multimedia. Anyway, it was a closed shop in Sydney, but by 1955, radiophysics had moved on to other things: radio astronomy, aircraft landing systems, and even rainmaking, which wasn't so silly, because a lot of the scattering issues with radar led into that, and Pearcey was an expert in that area. Anyway, other computers were coming to Sydney, so the huge computer, still the only working computer in Australia. They turned it off, dismantled it, and one of my favourite pictures, they shipped it to Melbourne down the Hume Highway. And I'm always impressed by the fact that Maston Beard, who was the engineer, despite the fact that he's, I'm not sure if it's Wagga or Gunda guy, is nevertheless fully equipped with a tie and a tweed jacket. What would an engineer wear in those days, even in the Australian, on the edge of the road? The road does look sealed there. I'm not sure it's sealed all the way. Here at the University of Melbourne, the computer became the centrepiece of a new computation laboratory, which was established in the old physics or natural philosophy building, and its mission was to provide a computing service to the university and to CSIRO and to the wider community, and also to undertake research and teaching in the new discipline. Thus, the University of Melbourne can claim to have established one of the very first fully fledged computer science departments in the world. I think we agree on that, don't we? On arrival, the computer was reassembled and renamed CIRAC, which is a name it's had ever since, and its looming grey presence, like a Stonehenge, I described it on the ABC yesterday, would dominate the computation laboratory for the next 9 years, and it provided the first computer service bureau in Australia. People queued to use it. Now, it had a speed and capacity that was laughable by today's standards. It had about 2,000 vacuum tubes or valves. valve, those things that used to glow in the back of our television and radio sets and get hot. It weighed a couple of tonnes and it required about 35 kilowatts of power, which is the power of most of a street. It operated about 500 to 1,000 operations a second, about 0.001 megahertz in today's terms, and it had a memory of 2 kbytes and a disk drive of about 3 kbytes. There are the valves looking inside, that's in the museum. If we could just go back one, thanks. Rows and rows of them, all getting hot, and all taking their heaters. You can see it's quite nicely designed and laid out. And then the hard drive, the disk drive there, which is about 3 kbytes. Nevertheless, it was a giant leap forward. Now, there are already computers at the University of Melbourne, and we've got an image here of 2 of them. Yeah, these are computers. One of those is Betty Labey in the stats department, and at this time, and Barbara Ainsworth is an expert on these women computers around the place, here and overseas, these hidden figures who were figuring away, and they were equipped generally with a calculator. Sometimes you had to wind the handle, and if they were really fortunate, it had an electric motor. There were different brands there. I think one's a Matus and one's a Munro. And they would work away doing extended calculations, and they were called computers. And my calculation is that at best, because you had to write down the intermediate answers, that at best they'd operate about 1 operation per second. Now, CSIRO scientist Terry Holden, colleague, recounted he had a calculation that took him 3 months, which is about 1,000 hours, if you work for 100 days at 10 hours a day, roughly. And at the end, he realised he made a mistake right at the beginning, and which was a bit disappointing. So he was one who seized on this new machine because this computer could do in 1 hour what had taken him 3 months. And if you want to be sure about it, you could run it in the 2nd hour, just check that it was right. So people queued to use this wonderful new machine, and it was used for 700 projects over the following years, including nuclear physics calculations, financial calculations. The university provided housing loans to staff in those days. In those days, the university lent staff money. There has been some suggestion recently it's been the other way around. The planning of the state electricity network, which is really relevant when you consider the kind of work that PSC Foundation is pushing at the moment, of our need to plan our network for the future. The primitive SEC network was planned with this machine. Analysis of frequency of duration of droughts, structural engineering, solar radiation, and so on. Quite a few of those things be relevant today. And one of great significance was a project, some of the earliest numerical weather forecasts ever, and there were papers still written about that work. And of course, there were computer games and further computer music. And Frank Hurst, the first head of the new laboratory, is often overlooked, I think, in the history we've done, was a driving force, and he promoted the potential of computers within and without the university. We knew we were on something important, and we wanted everybody to know about it. And we had open days, public seminars. Victorian Computer Society was one of the founding parts of the ACS, the Australian Computer Society. So how did one program this new machine? There was no high-level language, not even C or even COBOL, Fortran. There was no assembler. One had to program in machine code, instruction by instruction, and that's what one did. And the library of useful subprograms was developed, and a copy of them could be spliced into your program tape, so you actually took that, made a duplicate on your program tape. And when running a program, temporary fixes sometimes could be, well, made by changing an instruction in the memory on the keyboard of the computer, but sometimes you could edit the program by filling a hole in with a piece of sticky tape. I think I've got a picture of that. There we are. Somebody's modified it, and if you're lucky, and only 1 bit, and there's a little punch that you could actually punch extra holes. Most often you have to reproduce the whole tape. If it all went well, your result was printed on a teletype attached to the console. And we have to realise in those days you had probably put a limited amount of data in, did a fair bit of computation for the time, and a limited answer. There wasn't high volume data processing. Later on there were other peripherals added. And there was great competition to write ingenious code that saved one or two instructions, and in the process of doing that, they violated every principle of software engineering. People wrote obscure, brilliant code, instructions used as data, data used as instructions, and they were totally unmaintainable. And so what was considered super programming then, we would not give students good marks for these days. But it was, in some sense, a personal computer because you sat and drove it. And if we look there, there's just the front of this machine and people leaning over the console, little little cathode ray tubes there, CSIRO scientists at work. One wrote a program, booked a time slot, sat at the console and drove the machine through the program. And if necessary, could stop it and step by step. And so we could see each of those, I think in the next image, same people, I think. There, somebody here punching his program on tape, somebody checking a tape, somebody leaning over the console in the computation lab. So the user community was limited to those who could do this, which is not a large number of people. Some people found it their true vocation and went on to establish the industry. But by the late 50s, Jeff Hill, the first super programmer, had developed a high-level language, even in 2K, called Interprogram, and Interprogram looked very like BASIC, which was constructed later. And this opened up a whole new field of people. Final year physics students could use this to do some of their calculations. It was an extraordinary achievement to build a high-level language in that. He had to use paper tape and some intermediate storage, I think. And we've got Interprogram manual here somewhere. That's the original CIRAC manual. We've got manuals for all these things. So anyway, it worked on this machine for years, remarkably reliably, but by 1960s, it's the oldest working computer in the world, and in 1964, 15 years after it first operated, it was turned off, and we have a picture of the sad moment when Frank pulled the big switch, and as Kay said, it sounded as if something had died. It was the end of an era of those pre-1950 machines. We're now the computation department. The university had a second-generation transistorised computer, an IBM 7044 with a large number of magnetic tapes, no disk, and the language choice was generally Fortran and its variants. And for technically minded, it had a memory of 32K 36-bit words, about 150K bytes. This was 70 times the capacity of CIRAC. Surely all we'll ever need. Nevertheless, shortly after its arrival, I remember a rumour went round that Roger Seebeck, a researcher in forestry, had already written a program that filled the memory. Where would it end, we asked? Would they never be satisfied? He'd filled the memory already. We've now entered what I call the Oracle or Holy Shrine era of computing. With CIRAC, one interacted directly with a computer. These new mainframe computers were kept safe in an air-conditioned space, safe from mere mortals, although you could sometimes look at them through a window. Before consulting the Oracle, one prepared one's program on a card punch machine. This was the impersonal computer. And submitted the deck of cards with due deference, and submitted was the word. You submitted it to the computer for approval. And you handed it in the door of the Holy Shrine, and the attendants in some of these places were even thoughtfully equipped with white gowns to wear while they attended the Oracle. So people smiling, I can remember these days. And you'd come back later nervously to see how the Oracle had passed judgment on your offering. And all too often you found a message that said something like, execution denied, no logic. And you'd sinned with a misplaced comma or something else, and suitably advised you go away guiltily and try to do better next time. And your results came out usually on fanfold paper, which came out of these monstrously loud printing machines. Now, these machines have magnetic tape, so you could actually store quantities of data, although searching up and down was pretty slow. And we've now moved to the era where people started in business to refer to it as EDP, electronic data processing. Not computation anymore, processing data was what it was all about. And that was pretty tricky because you couldn't actually modify the tape once it had been written. You had to read the tape, do some modification in the machine and write a new tape. And if the operator who had to juggle this with the new and the old and so on got it wrong, you could end up with nothing on the tape. And as they used to say, on a cleared tape, you could seek forever. So during the 60s, as well as increasing demand for this computing, for admin and research, undergraduate use increased and we had high-speed compilers for them. But the main thing you had to do to put material into these machines was a key punch, and that became the user interface, and they were a limited resource. I think we probably got one here. So you actually sat and clonk, 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 and you queued to use the key punch. So this wasn't that good, really, from a user point of view, but fortunately in the late 1960s, mini computers started to appear. And the first of these in Australia was the DEC PDP-8, acquired by David Dewhurst, a pioneering biophysicist, whose contribution to computing and biophysics, and also, I have to say, the original conception of the bionic ear, is too often overlooked. There's David with a PDP-8 behind him. We got one of these in the computation department as soon as possible because we could just afford it, and you could use them one-on-one, and you could plug things into them, and so you could play around with the way you couldn't with the mainframe computer. And so these were our servants, whereas we felt we were servants to the big machine. Anyway, we were still doing all this in the computation department, but by 1970 we had to separate the operation, and the computer centre was set up, and we spun off the academic department. Alan Bell became control of a new computer centre, and it had control data cyber machines, and a significant development in that period was the availability of SPSS, which was a stats package for the social scientists, which meant a whole new raft of people started to realise they could use these new computers because often they prepared some, I have to say, sometimes ill-thought questionnaires or surveys. Somehow if they brought them along and put them through SPSS, everything would become right. And particularly their thesis would look very impressive with a bit of line printer paper attached to it. And so that was opened up even more widely. And we still had to use car punch machines. Now, fortunately, by 1974, Monash had done something really smart and developed Monex, which was a mini-computer-based system for schools and universities, well, primarily for schools, but we used it here. We called them scubas, and that meant that students didn't have to use a key punch machine. They could use cards, the cards were one card per program statement, and you either marked them with a black pencil or you pushed out the chads, and we've got enough of those for you to have one each as a little souvenir. And you remember the hanging chads in the Florida, in the 2000 US elections? We had lots of hanging chads. And the black lead pencil wasn't very satisfactory. When I was teaching prisoners at Pentridge using one of these, the printer kept rubbing out the black marks, and the prisoners thought their programs were being unfairly judged, and some of them got quite stroppy about it. So In the 70s, increased capability to connect workstations or dumb terminals, which are not much more than a TV set with a keyboard, and you could now edit and execute your programs without using the cards or visit the computer centre. Central computer had to be multi-user time-sharing to accommodate it. And many kinds of word processing became available and so on, and successively we built networks to handle these terminals. And if you were really fortunate, you could go home with an acoustic coupler and communicate over the telephone line. There is an acoustic, we've got several of these, but the foam that goes around, you put your telephone handset, people don't probably realise, telephone handsets used to have a microphone on one end and a little speaker on the other, and you plug them in there, you shut the box, plugged it into your telephone line, and you could communicate at probably about 300 if you were lucky. And this was because Telstra or Telecom or whatever it was in those days would not allow you to connect something directly to a telephone line. You had to connect acoustically. And in the audience here we have the person who led the push to change the rules at Telstra, and that's Wayne Fitzsimmons, who actually got them to admit that they had no reason to stop us using modems, our own modems, connected to the line. That's another piece of history. Anyway, ultimately, with the 80s, the arrival of the personal computer, which are updates on the terminals, because they now had a processor in them, a computer on everybody's desk became a possibility, and follow Professor Poole's landmark report in 1984 on the future of academic computing, that more or less became university policy. And so these things could do word processing, so word processing, processors and specials disappeared, and we then went even more deeply into networks, and Richard's going to talk about some of this, but at one stage the University of Melbourne was on the top 10 of all wired institutions in the country after the banks and the tax office, I think. Anyway, in the late 80s, the universities got together and developed ARNet, and staff in the department here played a leading role in that. And Richard Gillespie is going to talk about that now. But in closing, I should mention that in this building on Wednesday evening, Professor Michelle Simmons IO will present the PSC Oration, the 2023. And I see parallels with the brave pioneering efforts of Trevor Pearcey and his colleagues in the late 40s that launched Australia early into the digital age. 75 years later, the world-leading efforts of Professor Simmons and the team are helping to position us to capitalise on the possibilities of quantum computing. As we said back in the 60s, when Roger Seebeck filled the memory, when will it all end?
Thank you very much, Peter. Richard.
Thanks, Justin. Just wait for my slides to come up. There we go. Well, Peter's really given a kind of insider's account, I suppose, and as an historian of science and technology, mine is rather more a sort of an outsider's account. What I want to do, as Peter said, is focus more on the development of networks within the university, across Australia, and then the development of international networks. And in 1991, a computing technical writer from the US, Carl Malamud, spent 6 months in visiting 56 cities in 21 countries, talking with technicians, programmers, and network developers who were building the early years of the internet. And his 1992 book, A Technical Travelogue, was just that, a travelogue, combining technical descriptions, interviews, institutional assessments, restaurant reviews, provides a fascinating snapshot of the state of computer networks and the nascent internet. He came, of course, to Melbourne and to talk to people at the university, the computer centre and in computer science department, and he observed, this is one of those operations that has everything you want, The Information Technology Centre has regular, frequent schedule of training classes, extensive documentation, a custom programming group, a proactive help desk, spacious labs, and a trouble ticket system. This is great for the university community, but certainly posed a challenge for the digital tourist. After all, what can you say about a place that does everything right? So in fact, he spent a lot more time talking about some of the other Australian universities than he did about Melbourne. So in relating the development of computer networks at the university and beyond, I'll focus really just on two people. Peter Poole, the Foundation Professor of Computer Science, and Robert Ells, the programmer at the Computer Science Department, who became the linchpin in the development of Australian computer networks. Now, I'm conscious in focusing on two people, I'm leaving out a whole swathe of other people who played as critical roles around those two, but it allows me to it has the virtue of keeping this talk to time. Peter Poole, a formal portrait and a rather informal portrait in the machine room in Computer Science Department with a beer or glass of wine in his hand. Peter was originally a science teacher from Queensland and had undertaken a PhD in physics at the University of Sydney using Ciliac, which was the second digital computer in Australia after CIRAC. Attracted from physics into computing, he taught in the new Computer Science Department at Sydney, then moved to Britain to work on computing facilities at the UK Atomic Energy Authority, and then to a teaching position in computer science at the University of Colorado at Boulder. He was asked to apply for the Foundation Chair of Computer Science at the University of Melbourne when it was determined to have one in 1974. So Poole visited in early 1974, primarily motivated to be able to visit family back in Queensland as much as the job. And when he spoke to people in the department before meeting senior university people, he said, I came to the conclusion that there's no way I'd touch this job with a 40-foot pole because the department was in very cramped quarters and under-resourced to the point of idiocy. But he was obliged to do the job interview the next day, which turned out to be to the entire academic board of about 50 professors. It was the way you did job interviews back then. He was assured by the Deputy Vice-Chancellor and physicist David Carrow that the university would not be making a decision for several months, so no pressure. Poole had a knack, I think, for both seeing the future and being able to convey the urgency of that vision. After lunch, he was invited to meet the Vice-Chancellor, who, after some small talk, promptly offered him the position. Poole said, whoa, before we, this is too fast. He made it clear he would only accept the university if the university committed additional resources. These included 3 additional academic staff positions, a technical programmer, and the purchase of a powerful mini computer. He was adamant that an effective computer science department could not just rely on a central computing facility like where the mainframe had gone to the computer centre, as important as that was as well. He arrived in 1975, the following year, and in addition to the new academic positions, he made 2 significant acquisitions. The department purchased an Interdata 832, a 32-bit mini computer, chosen because it had an operating system that could support multiple consoles and time sharing. It came with an impressive 256 kilobytes of memory and 2 40 megabyte disk platter drives and 24 terminal ports. Undergraduate students would continue to use the Central University Computer Centre facilities, but third-year students and above had access to the Interdata, getting hands-on experience at hardware level. Poole's second notable acquisition was Robert Ells. Poole had taught Ells in a software engineering subject that Ells was taking as part of his combined law and BA honours degree. Ells' talent for programming stood out, and Poole offered him a part-time job initially as the department's programmer while he completed his law studies. His appointment did create a headache for human resources. Poole recalled, programmers, according to the rule of the university, started at 9 o'clock in the morning and went home at 5 o'clock at night. Robert Ells didn't work that way. Robert came to work at 6 o'clock at night and worked through until 6 o'clock in the morning. And in the process, his output was just phenomenal. Poole's weight was brought to bear until the HR department finally acquiesced. Now, based on his experience in the US, Poole was keen to adopt the Unix operating system as it could readily support multiple consoles and time sharing, and it was really becoming the operating system of choice for computer science departments. Developed in the Bell Labs, a version of Unix suitable for academic teaching and research was developed at the University of California at Berkeley and distributed widely as Unix Berkeley software distribution. Els worked with computer scientists at the University of Wollongong who were writing a portable version of Unix operating system for their Interdata computer and implemented this on the Interdata 832. Then in 1979, Poole and the Department of Meteorology developed a joint proposal for the acquisition of a powerful VAX 11780 mini-computer. Meteorology would use the computer for data analysis at night, while computer science would use it for undergraduate teaching during the day. And you can see the banks of the memory and processing unit, central processing unit on the left there, and the Andrew Mac at the terminal, and then some of the disk platter units like washing machines immediately behind for memory storage. Poole sent Els to the US to work with the team at Berkeley on their development of Unix, and his programming contributions to the development of the Unix BSD would be acknowledged in the updated versions. The VAX 11780 came with 1.5 megabytes of memory and two 67 megabyte disk drives. You can see they've got more by the time of that photo. With the Interdata and the VAX 11780, the computer science department was perfectly placed to establish teaching labs where students could use terminals to log into the computers. Students flocked to the new courses. Suddenly, bright students who previously did research degrees in maths, statistics and physics were choosing computer science instead. 100 EFTSU, effective full-time student units, doubled quickly to 200, forcing the university to initiate an inquiry. And ever a forceful negotiator, Poole argued that the university would lag behind if it did not support the effective creation of a leading computer science department. Poole managed to actually have the department's cap raised to 240, where initially they were trying to limit it from the 200. Creating an efficient and reliable network within computer science department was as important as the computers. And there's a diagram showing the connections between all of the computers in the department at the time, and then across on the right into the computer centres, cyber computers as well. Building the network was undertaken by engineer Yuri Semkiw and other technical staff. By 1983, computer science had three teaching labs with 62 terminals connected via a Gandalf, a serial port you can see on the right, switch that linked a series of computers. These systems were also linked by an Ethernet network with communication lines to the computer centre and its computers. In the early 1980s, Peter Poole returned from a trip to the US, announcing that he had seen the future and that everyone would soon have a computer on their desk, do their own word processing and have access to mainframes from their desks. He had visited the famous Xerox Park in Palo Alto and seen a lab full of Xerox Alto microcomputers with upper and lower case, graphical user interface, and connected by Ethernet to printers and other peripherals. These, of course, then went on to inspire the development of the Mac. Computing was quickly becoming so integral to university teaching, research, administration that a more strategic approach was urgently needed. By the early 1980s, there were computers in many departments, including electrical engineering, mechanical engineering, physics, anatomy, physiology, we mentioned David Dewhurst, psychology, and otolaryngology, where it was being used for the development of the bionic ear. In 1983, Poole chaired a working group of senior administrators, computer users and academics. Peter was one of the members of that working group to develop a comprehensive strategic plan that looked holistically at future requirements and effective methods to adapt to rapidly changing technology. And Melbourne was the first university in Australia to develop such a plan. Essentially, the plan embraced the idea that there would be a rapid devolution from central facilities to powerful desktop computers, similar in power, in fact, to the mainframe VAX. And it set out a clear vision. It says that as a major recommendation of the working group that all machines on campus should be able to communicate with each other through a campus-wide network of adequate speed and via connections to other networks to machines elsewhere in Australia and the world. The target is the ability for someone sitting at a personal workstation to access information and services wherever they may be located, to look up and transfer data, and to communicate with other people on and off the campus. And that was the vision that then informed the planning for the subsequent years. 6 weeks later, after that report, the Apple Mac, coincidentally, was released in the US. And the computer science department quickly purchased 20 for its labs. Yuri Semkiw and colleagues in the department developed a network gateway that would link the Macs to the department's network. And in 1988, a commercial version, Multigate, was developed in partnership with a local computer company and sold internationally, including to Apple headquarters in the US. One other commercial aspect I think should be mentioned briefly as well. Peter Poole had established also a systems development group in 1983 to explore commercial development of the department's research in software engineering. The major project became a fast retrieval software for large data sets based on search algorithms developed by Ron Sachs-Davis at RMIT and Rao Kotagiri. A beta version of the database was installed at Museum Victoria in early 1984 to test the database. In 1986, research was spun off as a separate company, Knowledge Engineering, which received an inaugural Commonwealth Government R&D grant of about $500,000. Subsequent versions of that software, EMU for Electronic Museum, are now used by major museums and galleries around the world. It's now owned by a Swedish library informatics company, Axial, but the Asia Pacific office is just down off Lygon Street. From the early 80s, servers started to be linked by phone lines to networks of computers in other countries. These were not permanent links, but achieved typically by calling up and sending data once a day or more often as required. Sitting in Melbourne and working almost exclusively at night, Robert Ells quickly began linking the Melbourne department to a range of emerging, although only loosely connected networks. ACSNet in Australia, linking mainly computer science departments, CSIROnet, which was the CSIRO network, which Trevor Pearcey had been involved in developing, ARPANET, which was the US network supported by the National Science Foundation, and CSNet, the network of US computer science departments. Robert Ells notoriously avoided ever having his photograph taken, so these are the only two photos that have ever managed to quite emerge of Robert. The link between these networks was not straightforward. It required an intimate knowledge of which servers in which university or agency were acting as nodes of the network, and a clear picture of the paths that files or mail would need to take in order to reach the desired recipient. Writing in the Australian Unix user group newsletter in '85, Ells attempted to explain how to ensure that mail reached the intended recipient. You had to do complex paths that actually described the different computers that the mail was going through, and then hopefully the reverse. In doing reply, you needed to follow the reverse, although it never quite worked like that. Because what happens is the managers of these emerging domains tried to program their systems to capture as much of the passing traffic as seemed relevant by looking for variant but related addresses. This could help, but it could also cause problems. With lots of, Al says, with lots of hosts out there all grabbing onto every address as it flies past and trying hard to interpret as an address that means something special in their particular world, if you try anything fancy at all, one of those mail programs is going to bite on your mail. Goodbye mail. Once one computer's taken it, that's it. Ells began collaborating with Torben Nielsen, a computer specialist at the University of Hawaii, and Australia's Overseas Telecommunications Corporation to try and establish a permanent real-time internet link between Melbourne and Hawaii. and from there to the University of California, Berkeley, and hence out to all of the US networks. OTC established a 64 kilobyte per second satellite connection between its Oxford Falls Earth Station in Sydney and the Sunset Beach Earth Station in Hawaii, and Ells and Nielsen started testing their connections to the link, which used TCP/IP protocol supported by routers at each end. And then finally, on Saturday the 24th of June 1989 at 3:26 p.m, Ells received a message from Nielsen in Hawaii, subject link up. Guess this means the link is up. Hey, nice to see it at last. It took them a few more days, but essentially it became stable shortly after the internet had come to Australia. The creation of the internet in the US had necessitated the creation of a new addressing system to get around the existing complexities of routing through designated servers. So a domain name system was created with .com, .net, .gov, .org added to country names. Because he was known so well in the US, Robert Ells was privately assigned control of .au, and he then assigned .gov.au, .org.au, and .net.au to others in Australia. He retained control of registration of domain names for .com.au because he could see that this was the domain where controversies would most likely arise, and he developed rules to try and create a level playing field for companies. However, within a few years, the demand by businesses for the assigning of .com.au names had overwhelmed Ells' ability to manage the system in his spare time. The clamour became such that Ells agreed to assign .com.au to Melbourne IT, a company that had previously been established by the university to develop commercialisation opportunities in telecommunications and IT. Melbourne IT developed the software to manage the registry, and in 1999 the company was floated fortuitously just at the peak of the dot-com bubble. The university raised some $80 million from the float just before the dot-com crash of March 2000. And it remained a rather controversial issue as the way that whole share issuing process was undertaken, with a Four Corners program devoted to it. A final mention then of an unexpected digital innovation. Robert Ells had been a cricket fan from childhood, scoring test matches while watching them on TV. With the advent of the internet, he quickly became active in a Usenet group, rec.sport.cricket. Sitting in his office watching TV coverage of the Sydney Test match in January 1992, Shane Warne's debut in Test cricket actually, he began a live internet commentary on the game. There's a poor screenshot of it. Initially he posted summaries each hour, but quickly realised it was actually easier to do ball-by-ball description, especially because cricket had brief action followed by gaps while the bowler went back to bowl. Within a few months, Indian computer science students and cricket fanatics in the US, inspired by Ells, had taken up the baton, and in 1993, Cricinfo was launched as a bot on internet relay chat, so you could just literally have it sitting on your screen with a blow-by-blow account. Ells had pioneered online text commentary for cricket, and indeed for sport generally. It would be another 6 years before the US National Football League introduced play-by-play commentary. It's an example of the kind of unexpected developments that come out of that kind of obsession and capacity. So finally then, I think innovation emerged as a complex of technology, of people, of organisational culture and networks locally, nationally and globally. And I think it can be claimed that the organisational culture and human and technical networks nurtured at the university in this earlier period contributed significantly to the university's global position today. Melbourne Connect is a descendant of the innovation of this earlier period. And I think sometimes, I've been reflecting on it, that we tend to think of looking at traditions within disciplines within a university, whether it be in fluid mechanics, in mechanical engineering, or in natural language processing, or whatever it might be in whatever field. And it's easier to see those kind of connections from one generation to the next. But I think in the case of the kind of networking and this, you call it almost a technological culture that gets embedded in a university, it's a little harder to sort of see the archaeology and to show the archaeological traces of that. But I think it actually is as significant as those more sort of obvious sort of intellectual traditions. We tend to focus on here's the latest strategy without necessarily seeing the deeper cultural streams that sort of sit underneath those strategies across generations. Thank you.
Thank you. There are so many questions I want to ask, but I'll give the audience the courtesy first. Is there anything anyone would like to put to Richard or Peter? We sit in silence. I'll share a moment. You had the photo of Andrew Mack, and I really liked that photo because you also had 1980 with Peter Poole with the VAX 11780 in the background, and there it was 11 years later in the background for the photo of Andrew. He was actually not sitting at a terminal, he was sitting at a Sun 360, which I think was about a 6 megahertz machine, so about 6 times the speed of the VAX, and with a bit more memory. And yet the VAX in the background was still a workhorse undergraduate machine after 11 or 12 years. So there's a lovely sort of transition there. But something I'm also very conscious of, or reminded of in your talk, is that because the VAX was so loaded during the day by students, incredibly loaded, if we ran a database system that students used, for example, for the database subject, and a query would take 24 hours to run. So you'd have to issue it and then sort of come back. So us PhD candidates did our work at night. So I used to sit there through the night. Robert would be downstairs. I've got another picture of him, by the way, number 3. We'd sit there through the night. And 1987, we had the dial-up internet to Sizemo. And I'd have the radio on, the ABC. Even then, they had the sort of nighttime chat show. And we started getting these messages coming through from the US. It's a disaster. It's Black Friday. The markets have crashed. It's a complete disaster. Everything's wiped out. The economy's going to fall over. Wall Street fell. I can't remember, about 26% or something that day in October 1987. I was going to say 1887. I knew that wasn't right. About 4 hours later, it came on the ABC, sort of towards morning. And so it was such an illustration that was that first real sense of what the networking had brought, that I knew this news 4 hours before, the general public knew it, probably before the radio people knew it because of the nature of the feeds that they were getting. And this instant delivery, and for the first time ever, in my experience, news delivered democratically, not through a news organisation, but from person to person. So it was just this very sudden, awakening of change. So you gave the sort of illustration of the cricket scores as being something else that just emerged organically. That was a very sharp one, and I think a lot of people, certainly around the school at the time, noticed that change going on. That wasn't really a question, but I wanted to just reflect.
Just wondering, were the early computers error prone? Were they error corrected? I mean, that's a big issue when you're working on modern or.
I've got a lapel mic. Is that working still? Yep. The answer is they were definitely error prone. One of the things that we hardly ever talk about is error correction. And Maurice Wilkes, one of the great pioneers, says that the two inventions, stored program machine, error correction. It's extraordinary that we can send billions and billions of bytes of data and we just assume it's correct. We've never done anything in history that's that accurate. It's just remarkable that it works. in the early days on something like CIRAC, you probably after an hour, you're probably a good idea to run it again. We did have this particular problem with CIRAC that it was located with a statatron, a Van de Graaff generator on one side, and out across the laneway was where the university cyclotron was. Now, when the statatron, which was about 500,000 volts, sparked to ground, it used to grow bits in our memory. And when they turned on the cyclotron, which had a big tramways generator to drive the magnet, the power used to go down and we used to lose bits from the memory, but they never cancelled each other out. And so, you're right, the early computers were error prone. They didn't, later on the first thing you had was a parity bit, which just helped and so on. But I mean, every now and then I step back and think this is just extraordinary that I've loaded images, text and so on. And I loaded something today actually for one of the images, and on one device I thought, wow, have I seen a data error here? And it was the device sort of loaded on something else and it was okay. But it's one of the things I think it's perhaps hard to contemplate that nothing mechanical has ever been as reliable. Nothing mechanical has ever done billions of operations in its lifetime. And it all happened and it just was almost under the radar. And I mean, Hamming and so on was one of the earlier things. He came to Melbourne. We had, he visited the department and so on, and we talked about these things way back. But they were unreliable.
I'm going to add slightly to that anecdote, if this microphone is working. Thank you. Which is that even in the early 90s, when the first really compact, large, when I say large, 160 megabyte disk drives started to appear for a mere, $10,000 or something. They were bargain basement. They were prone to cosmic ray errors. So even though there was error correction, even at that point, these drives, which were incredibly sparse by today's standards, actually if you wrote a really large data file and ran a long experiment on it, even then, every now and again, you would get an error by the end, or a fail, and it was pure cosmic ray error. And this explanation hadn't occurred to me, but a friend who was doing a PhD in physics said, we've talked about using them as cosmic ray detectors, just putting them in different parts of the building to see how vulnerable things are. Of course, they actually had better ones, but the joke was that ground floor was a lot better than the 7th floor of the physics building for running your Sun computer. They got better. Wayne.
Thanks, Justin. Just two comments. You reminded me of the transmission from the US of the 1987 collapse on the NYSE. Coincidentally, Senator John Button, the Minister for Industry, was in Boston that day, and I was hosting him at a big dinner that night of all the top executives in the IT world, because I was involved there, and he never forgot it because he was stunned, and he'd called Bob Hawke to tell him, I think. Just one other, Peter alluded to the fact that I did talk to Telecom about this right to connect modems, and it's just an anecdote of the history of the industry at that time. This took place in 1978, and I was running a mini computer company whose name was not mentioned tonight, and I could never sell to Melbourne Uni, but I got my edge. But we formed an industry association. It was called ACESA, the Australian Computer Equipment Suppliers Association, now known as AIIA. And it was all formed in secret because we were worried that the Labor government would see it as a conspiracy between all the computer manufacturers to screw Australia over. Well, it wasn't quite that. It was a lobby group, but the main thing why I joined was, in fact, running this mini computer company. We couldn't sell modems. We had to go to Telstra and they'd make you jump through hoops. So in the end, we looked up the legislation and the regulation, and there were no regulations at all. So I went down to see the CEO of Telecom at the time, whose name escaped me. He was a great guy. I walked in the door. He didn't say, he said, I know why you're here. He said, there is no regulations, but you need to talk to Jim. So he delegated me to go down to see Jim, who was an engineer, whose son had died because he'd electrocuted standing bare feet on the top of a galvanised iron room with an with an electric drill that wasn't earthed. And he was paranoid that these computer engineers would have they wouldn't have no idea about electrical shorts and anything like that, and so they were unqualified, and only he and his group at Telecom could do this. Anyway, they changed the rules.
Thanks, Wayne. Questions? Jordan.
Sure. So you've talked about the history of the computers that had very limited memory, and the art and the skill of trying to create programs that would work in that memory. And now we look back over, say, certainly the last 15 years, if not a little bit more, we've had the luxury of plenty of memory, and the art of programming has changed significantly. But now, as we look forward into things like space, where we're going to take our luxury of resources but put them in very unsupported environments, and there's a return to people thinking about this whole art of how do you get the most efficient program, not just for the memory space but also the energy consumption. Do you see any parallels or opportunities that Australia could try and follow or pursue in this evolution?
That's a hard question. Well, I mean, one of the obvious things that we should think about is our unusual elements that we can dig out of the ground in Australia, and whether or not there's something there in terms of other materials than the standard silicon and the standard doping and all those kind of things. I guess as an old person, I'm still trying to catch up with the fact that they reckon in 2015 there were more transistors in the world than there were leaves on all the trees, which is pretty frightening. And winter or summer? Oh, it's different hemispheres. But I mean, that is pretty extraordinary if one thinks about that in the time. And so there's a technology which has come so far, so quickly, unbelievably quickly, and will come to a limit, as I'm sure Michelle's going to tell us on Wednesday night. But I'm not sure, I don't know enough about the physics to know whether or not we could do anything which would future-proof them in the way you suggest, or whether it's going to be a redundancy issue in terms of the fact that we can now build multiple things that fail. I mean, the big disk farms from around the world are not built out of high-quality components. They're built out of the cheapest disk drives and things that equivalent that they can find, on the basis that there's redundancy, and so they're not gold-plated. And maybe it's a redundancy issue. I don't know. So I really don't know enough physics.
I don't know how to answer. I am conscious of time, but I will observe that I've got well over 1 trillion transistors in my pocket. So that's I don't know how many trees that is.
Yeah.
But I will call time there. Thank you all very much for joining us today. It's been an absolute pleasure. Please join me in thanking again Richard and Peter for their contribution.